Okay, so what did we learn there? We learned that we can figure out how much space a particular variable type takes up by using the size of operator. We can also find the address that a variable is stored at by preceding the variable name with an ampersand. So, what's all the to-do about these pointers? Why are they important? Well, it goes back to something you learned earlier in the class, calling by reference versus calling by value. Let's take a look at some code. If you look at this code, you'll see prototypes here, and then you'll see those functions down below the main. One of them is called doublet1, and the other one is called doublet2. Each function is going to double the number sent to it. We're going to start here, of course, in main, and we're going to initialize the integer variable number with 10. We print out, before a call to double it, number 1, the number was, and then print out the number. Then we're going to call double it, sending that variable. Then it's going to return after the number is doubled by double it number 1. And then it's going to return and says after the call, and it's going to report the value of the number. So we have the number here 10. We send it to double it. It's going to be doubled, so at that point it's going to be 20. And then it's going to return to the calling program and report its value. Now after we do that, it's going to say, okay, I'm getting ready to call double it 2 and report the value of it. It's going to call double it 2 and it's going to send the number. Double it 2 is going to double it. It's going to return it back to main, and it's going to report its value. Let's see what happens. Now, before the call to double it, the number was 10. That shouldn't surprise anyone. Then we called double it number 1 and sent it 10, the value in number. Double it got that value, doubled it, and then returned control back to main. And then we printed out after the call the value is, and it's 10. In other words, even though we doubled it in double it 1, the value didn't change in main. Okay. Now, since it wasn't a global, that really shouldn't surprise you. Now here, in the second part of it, we say before the call to double it 2, and we print out the value, which of course is 10. We call double it 2, and we send that value of 10 to double it 2. But notice right here, the parameter in double it 2 is preceded by an ampersand. Remember earlier we said that if a variable is preceded by an ampersand, it really is the location of that variable. So we're sending actually the location of number to double it 2. Okay, so then that means num is no longer a value, it's an address. And so that address says double it. So whatever's at that address is going to be doubled. So 10 doubled is 20. And then it's going to return control back to main, and it says after the call the value is, and it's going to print out the value. Notice in the output, after the call the number is 20. Now this is a way to avoid using globals. We can send a variable by reference. How do we do that? Well, we precede the variable with an ampersand. And the ampersand says, I don't want the value there, I want the address. And then any further use of that variable name is going to refer to an address. And so the contents of that address are going to be doubled. All right, that was a nice review of calling by reference versus calling by value. And I think if you understand that calling by reference utilizes a memory address, I think you can begin to see why pointers are going to be so important, because pointers hold memory addresses. And so we'll go ahead and dig in deeper into pointers, and we'll learn in this section, after we declare a variable, how can we access its address? I think you already know the answer to that. We prepend it with an ampersand. Secondly, how do we declare and assign a pointer variable? We'll dig into that. And third, how do we access the value that we store at that address? So for instance, if x is equal to 3, how do we access that 3 using the address? Well, in order to figure all this out, let's go to this URL and examine the code there. Okay, by now you should be familiar with all this. This is boilerplate C++. We're always going to have it there. And here's where all the action happens in main. First of all, we declare an integer variable called x and assign it a value of 10. This on line 7 is brand new. This is a declaration of an integer pointer. Notice we have int, and we have this asterisk, and this variable that we can make up the name, we just call it PTR because it makes sense for pointer. And so this is going to hold the address to some integer memory. We assign its initial value as null pointer. Now this is very important. Whenever you create a pointer, you should initialize it. You shouldn't just leave it uninitialized because wacky things can happen. So the null pointer is the null value or 0. So that initializes it, makes it nice and safe. But the very next line, line 9, prepends that x variable that we declared in line 6 with an ampersand, which you will recall extracts the address from that variable and it assigns it to that pointer. Now we really need to know that it's an integer pointer because the integer pointer knows that it's going to reserve 4 spaces for an integer. Remember, 8 spaces for a double, etc. So we need to give the pointer a type so it knows how many memory locations to save. So we declare an integer pointer. It's going to point to an integer. We initialize it with the 0 value, but then right away we reassign it. We send the address of the integer variable x by using the ampersand in front of it to that pointer. Now we're going to report some values. So we print out that the value of x is, and we just dump out the variable. This is an interesting part, and we say, and its address is, and we print out the address using the ampersand x. The next line repeats, but the interesting thing about this, even though it repeats the value of x, notice it's repeating the value of x by taking the pointer and putting an asterisk in front of it. What that says is, find the value pointed to by that pointer. Whenever you prepend a pointer with an asterisk, you are asking for the value at that address. This is very important to understand because you can get lost in all of these asterisks, etc. Here, this asterisk is saying, you know what, this PTR is going to be a pointer. That's the purpose of this asterisk. Furthermore, it's going to be a pointer towards an integer. Here, without that int in front of it, it has a different meaning. It's saying, go get the value pointed to by this pointer. Let that soak in a little bit. This is saying, go get the value at the location pointed to by this pointer. And then it further prints out its address just by printing out PTR. Notice there's no asterisk there because PTR is a variable that holds a pointer to an int. I understand it can get very confusing, but this expression is when you're declaring a pointer variable, a variable to hold an address. You say the type, and then you put the asterisk in front of it, and then whatever you want to name it. Here we're initializing it to 0, and then we're reassigning it the address of x. But when you want to print out the value stored at that address, you use that pointer variable, and you precede it with an asterisk. Now, this x is equivalent to this asterisk pointer. Because remember, the address of x was assigned to the pointer because we used this ampersand in front of the x. And so pointer has the address of x. But when we put an asterisk in front of it, we're saying, give me the value at that location. And then if we just use the pointer without an asterisk, we're actually just printing out the address. And then here we're reassigning it. Check this out. We're saying 100, I want to assign you to the value at that location. So we're going to see that. And then it's going to tell us, after we reassigned it, the value of x is, and notice it's x here, and its address is, and it tells us the address. And then it's going to show us the new value of x using this asterisk pointer, which we call the dereferencing operator or the indirection operator. So let's see it in action. The value of x is 10, its address is this long hexadecimal. Repeat, the value of x is 10, and that's using that dereferencing operator on the pointer, and its address is this, and that's just using the pointer variable. After reassignment, remember we said 100 is going to equal the dereferenced pointer, and it says the new value of x is 100, that's using the x variable, and its address is this new address. Very interesting. Kind of complex. Let that soak in. All right, that was some good stuff. We learned how to declare a pointer, and we learned that you have to declare the type of pointer that you're going to create. The reason for that is because that pointer is going to reserve a certain amount of space for integers and a certain amount of space for doubles and booleans and characters and shorts, etc. But it's going to point at the first address in that little block of memory. We found out that we accessed the value stored by that pointer by placing an asterisk in front of the pointer variable. And that asterisk is called the dereferencing or indirection operator. And it tells us, give me the value stored at that location. So let's learn more about blocks of memory by going to arrays. Now, before we jump into arrays, I want to make sure that it's crystal clear that when we talk about a pointer, we're talking about a memory address, and that will have a certain size. But the block of memory that it's pointing to will also have a certain size. For instance, if it's an integer pointer, it will have a size of 4 memory locations. If it's pointing to a double variable, then it's holding 8 memory locations. But in both cases, in the integer case and in the double case, the pointer itself is the same size. The pointer, that size, won't change whether you're pointing to a character or a short or an integer or a boolean. The pointer's size won't change, but the block of memory that it's pointing to will change. Now we'll make this clear by introducing how we deal with arrays, and hopefully you'll be able to sort that all out. In order to do that, let's go to this code as listed at the top of this slide. Okay, here we go. You'll see here in main, we've declared an integer array called numbers having 10 elements. Now remember, each integer is 4 memory locations or 4 bytes. If we have 10 integers, that's 10 times 4 or 40 bytes. 40 memory locations would be pointed to by a pointer. In the case of a double, remember each double takes up 8 bytes or 8 memory locations, and we have an array here called decimal that has 10 elements. 10 times 8 is 80. So we have 40 and 80, just these two declarations. 120 bytes it's pointing at. We call that a block of memory. So down here when we report, we're saying, okay, print out the size of this numbers array. If you'll recall that the name of an array is an address. Okay, so this is going to point to the block of integers pointed to by numbers. This second line on line 10, because numbers has an ampersand in front of it, is also going to print out the address. And that's what's going to be interesting here. You'll see numbers and ampersand numbers are going to print the same thing. And the size of this is going to be the size of the pointer. Now, down below here, we're going to print out decimal, which is the address point of the beginning of that array, that decimal array. And then here, we're going to ask for the size of that array. And it should be 80, because we have 10 elements, each element 8 bytes large. So the next line prints out the actual address and then the size of that address pointer. So let's run this. How interesting is this? Notice that the size of the numbers array turns out to be 40. Not a surprise. 4 bytes per integer, 10 integers, 10 integer array. So that's going to be a total of 40. But when we look at the size of the pointer, because that's the second line, the size of the address here, it turns out to be 8. 8 bytes long. Now, down here in the line 12, we ask for the size of the decimal array. Remember, we have 10 elements, each element 8 bytes long. 8 times 10 is 80. That's a block of 80. Together, 40 and 80 is 120, so we have 120 bytes reserved here. And then here, this is the address, the actual pointer. And we want to find the size of that, and again, it's just 8 bytes. Isn't that interesting?